Section 5.2, we're looking at area of plane figures. So we notice that we like to start with the idea of a unit square. A unit square is a square with sides equal to 1 unit of distance And so we notice that the size of a unit square depends on what measurement system we're using. So if we had a square that was 1 foot by 1 foot, that would be 1 square foot. Because we know we're just looking at that as 1 foot times 1 foot. If it was a meter by a meter, we would wind up having 1 square meter. And so you'll notice that when we're talking about areas, we're often thinking in terms of square units. So square feet, square meters, we could also have square centimeters. Oops. So in general, if we think of the idea of a square unit, we're just thinking in terms of these unit squares. So we notice that if we were going to look at something simple like a rectangle, if we were going to say this rectangle was 3 meters by 5 meters, we can imagine breaking it up as a bunch of unit squares. So we can imagine having it be 3 unit squares tall, 5 unit squares across, and so we could count. We notice that the area is 15 square meters just by counting. But you notice that counting can get increasingly problematic. And so what we can do instead is say area of a rectangle is length times width. And so we can abbreviate that as A equals L times W. And we notice that if we take 3 meters times 5 meters, we get 15 square meters. And so we can treat that the units, meters, kind of like we would treat a variable. So you notice that the units don't have any value in and of themselves, but we can treat them like variables when we're thinking about multiplying them. And so we notice that 3 meters times 5 meters, we get 15 square meters. So if we had something bigger, if we were going to look at a rectangle that was, say, 50 meters by 200 meters, we notice we really, really don't want to count up squares. And so we know the area is going to be 50 meters times 200 meters. We think 50 times 200 gives us 10,000. And so we get 10,000 square meters. Nice and neat. So for some of our basic shapes, we notice that for a triangle, with base B and height H, we know area equals 1/2 B times H. So if we have some arbitrary triangle with a height of H and a base of B, we know that its area has to be 1/2 base times height. And that actually comes from something we know about parallelograms. We notice that for a parallelogram, we can, let's redraw that parallelogram. For a parallelogram, we can imagine taking that triangle at the end and moving it over to the right side. And so we notice that if we have a parallelogram with side lengths A and B and height of H, we notice that we can move that triangle from the left to the right, and we notice that the area is going to end up being H times B. And with a bunch of trigonometry, we could actually figure out what H has to be, but that takes some trickier computations. So for parallelograms, if we want the area of a parallelogram, we'll be given the height. You also notice that we could also have done it, we could call it H1. We notice that if we looked at it from the other perspective, we could imagine height 2 being the distance between those two. Let's write it this way. We can imagine height 2 as being the distance from one A side to the other A side, and we notice that we could let's draw it this way. We can imagine moving that triangle to the other side of the parallelogram, and again, we wind up getting the area would be H2 times B. And so it's generally just an issue of which height is easier to calculate. We can usually do it either way with a parallelogram. And then we notice that if we know the area of the parallelogram, we notice that we can chop it in half to get a triangle. And so we notice that the area of the triangle is 1/2 of the base times the height. And so that's kind of where we get our area for a triangle from. For a trapezoid, with height H and bases B1 and B2, we know the area is going to be 1/2 B1 plus B2 times H. And so what we're noticing there is that if we know the height, we can imagine that we can chop off the bottom triangles and move them up to the top, and it's going to give us a rectangle. That's going to have height h and a width that's the average of the two bases. Then for a circle, the area is given by a equals pi times the radius squared. And so we notice that for a circle of radius 6, the area is going to be pi times 6 squared, and so we get 36 pi. And so you'll notice that we'll often write it just as 36 pi, especially if we need an exact number. If we said a circle has radius 2 centimeters, we'll make it 2 meters. We know the perimeter, the circumference. Circumference is equal to 2 times pi times 2 meters, gives us 4 pi meters. And then we notice 4 pi, that would be approximately 12.56 meters. We'll often use pi as approximately 3.14, winds up being convenient. And the area, oddly enough, is going to be pi times 2 meters squared. So we get pi times 4 square meters. And so we wind up getting 12.56 square meters. So then if we try looking at stranger shapes, composite shapes, again, we have to use logic and our basic shapes. If we had, for instance, a square with a circle on top of it, and we know the square is perhaps 8 inches by 8 inches, we notice that that forces the circle to have a radius of 4 inches. And so the area is going to be the area of the square plus the area of the semicircle. And so we're going to get 8 inches times 8 inches plus pi times 4 inches squared. And so we're going to get 64 square inches plus 16 pi square inches. And at that point, we would probably just leave it. We could get an approximation for that, but we're not too worried about that. If we had a rectangle with a rectangle cut out of it, so if we made that 12 meters by 8 meters, and then the internal units might be 8 meters by, like that, 8 meters by 6 meters, we notice that the area of the, let's make it, we'll want the area of that shaded region. The area is going to be the area of the outside region, so we're going to get 8 meters times 12 meters minus the blank region. So we're going to subtract 6 meters times 8 meters. So we get 96 square meters minus 48 square meters. And so we get 48 square meters. Similarly, if we said we had a rectangle with corners cut out, whoops. So if we imagine this was maybe 6, 6, 3, 3, and then all of these were 1s, we notice that the perimeter would be a little tricky, but the area, we're going to wind up getting, we actually have two ways we could do it. We notice we could think of it as being 8 units times 5 units. So the area of the rectangle, if we didn't have those corners cut out, minus those 4 1 unit by 1 unit shapes. And so you end up getting 40 minus 4 is 36 square units. Alternatively, we could do it chunk by chunk. We notice that we could break it up into rectangles. We notice that we have a 3 by 1 rectangle, another 3 by 1 rectangle, a 6 by 1 rectangle, another 6 by 1 rectangle, and then that interior rectangle is going to wind up being 4 by 1. And so we wind up getting, 4 by, wrong, just a second. It's going to end up being 6 times 3. Whoops. So we've got the 6 by 1. We've got the 3 times 1 plus the 3 times 1 plus the 6 times 1 plus the 6 times 1, and then the inside rectangle is going to be a nice, neat 6 by 3. Always be careful not to overthink things. And so we get 3 plus 3 plus 6 plus 6 plus 18. And so we get 36 square units again. Also notice that if you try doing it by two different routes, you should always get the same answer. Let's try one more of these. If we tried saying a rectangle on top of a trapezoid, and we said that the base of the trapezoid was 10 centimeters, and we know the rectangle is, let's make it 4 centimeters by 5 centimeters. We know that its area is going to be the area of that rectangle plus the area of the trapezoid equals 4 centimeters times 5 centimeters. Whoops, we also need the height of the trapezoid. Height of the trapezoid will make it 3 centimeters. So the area of the trapezoid, we're going to get 1/2 times 10 centimeters plus 4 centimeters. So we get the average of the top and bottom of the trapezoid times that height of 3 centimeters.
Hi, Dad.
Which gives us 20 square centimeters plus, that'll be 7 centimeters times 3 centimeters. So we get 20 centimeters squared plus 21 centimeters squared gives us 41 square centimeters.